In the previous tutorial, we looked at oxygen carriage in blood and why hemoglobin is so important. But I also mentioned the Bohr effect. And in this tutorial, we're going to look at how hemoglobin carries carbon dioxide and why it's so important. And I also want you to think a lot about bicarbonate. In the situation of CO2, you must think beyond the PaCO2. Fundamentals of Anesthesiology and Critical Care with me, your host, Pat Nelligan. Understanding gases and vapors. This tutorial is on carbon dioxide transport in blood. Welcome back. So far in this series, we've looked at the solubility of oxygen and carbon dioxide in plasma. We looked at the alveolar gas equation, the oxygen content of blood, oxygen transport and delivery, and the oxyhemoglobin dissociation curve. Now we're going to dig deep into carbon dioxide. In this tutorial, I'm going to talk about carbon dioxide content of blood, plasma, and extracellular fluid and delivery of carbon dioxide from the tissues back into the lungs. I'm going to start with a very short discussion about carbon dioxide and metabolism, the diffusion characteristics of carbon dioxide versus oxygen, how carbon dioxide interacts with hemoglobin, the Bohr and Haldane effects, what happens with acute and indeed chronic hypercarbia, and the impact of hypercarbia on bicarbonate. So let's start with carbon dioxide metabolism. The primary sources of energy in the body are carbohydrates, proteins, and fats. And the way we think of them as being metabolized to glucose, amino acids, and free fatty acids. And that is true, but in fact, they really are not metabolized to those endpoints. They're metabolized to carbon dioxide and water via the Krebs cycle with the intermediate step of acetyl coenzyme A. So everything that we eat ends up as carbon dioxide, but not every gram of substrate produces the same amount of carbon dioxide. For example, for every gram of carbohydrate that is metabolized, the same amount of oxygen is consumed versus CO2 produced, about 0.83 liters. So the respiratory quotient is 1. For protein, we consume a little bit more oxygen than we generate carbon dioxide, about 0.8. And for fat, it's significantly more oxygen consumed per carbon dioxide. Overall, when we average the amount of carbohydrate, protein, and fat that we consume, about 0.8 is the magic number for how much carbon dioxide is produced per unit oxygen. And that's why I keep saying that we consume 250 mils of oxygen per minute, but we produce only 200 mils of carbon dioxide. Obviously, that increases with activity. The more activity, the more oxygen consumed and the more carbon dioxide generated, but that ratio remains more or less the same until we run out of substrate. Oxygen diffuses from the alveoli to the blood and then to the tissues. Carbon dioxide diffuses in the opposite direction, from the tissues back into the blood and into the alveoli. So they're both diffusing. You might get the idea that the diffusion capacity for oxygen and carbon dioxide are similar, but they are absolutely not. Carbon dioxide is 20 times as soluble in blood and tissues as oxygen, as we saw in an earlier tutorial, but it also diffuses 20 times faster than oxygen through tissues and fluids. And although partial pressure gradients for CO2 are lower, CO2 equilibrates more rapidly across membranes. And as a consequence of this, any situation where there is impairment of diffusion, it impacts oxygen much more than carbon dioxide. An example of this is pulmonary fibrosis. I previously demonstrated the oxygen cascade where there was an enormous partial pressure difference between the alveoli and the mitochondria. With CO2, the gradients are very small in comparison due to the ease of diffusion and high solubility. So let's look at the gradients. The mitochondrial PCO2 is 6.5 kilopascals or 49 millimeters of mercury. The intracellular PCO2 is 6.3 kilopascals or 47 millimeters of mercury. The interstitial and venous CO2 are more or less the same at 6.1 kilopascals or 46 millimeters of mercury. The arterial CO2 is 5.3 kilopascals or 40 millimeters of mercury. The alveolar CO2 equalizes with the arterial CO2, so the partial pressure in alveoli is 5.3 kilopascals or 40 millimeters of mercury. The end expired or end tidal CO2, as I'll discuss in a minute, is 5.2 kilopascals or 39 millimeters of mercury. So you can see that the tissues are literally soaked with carbon dioxide, and there is only a tiny partial pressure gradient between the interstitial space and the venous space, with a little drop on the arterial side due to alveolar ventilation. Importantly, tidal breaths do not clear CO2 from the alveoli. They merely reduce it momentarily until more CO2 diffuses inwards. In this example, the yellow lines represent the expiratory CO2 as measured by capnography. And you can see that during exhalation, there is a slight fall in the alveolar CO2 tension that vents off the surplus CO2 per minute. At rest, for example, if 200 mils of carbon dioxide are produced and there are 10 breaths per minute, only 20 mils of carbon dioxide is exhaled for a 400 to 500 mil tidal volume. This point is the end expiratory PCO2, that is the end tidal CO2, the CO2 partial pressure at end expiration. That is the high point of expiratory CO2, and that's what we measure in the operating room and in the ICU when you see it on the monitor. But CO2 is leaving the alveoli during the entire course of expiration. So it starts here from pretty much zero baseline and then works its way up to the end tidal level. Importantly, the PCO2 in mixed expired gas is only 3.8% or 3.6 kilopascals, 27 millimeters of mercury. A lot of what you are exhaling, the majority of it, is air. It's oxygen and nitrogen with only 3.8% carbon dioxide. Now let's move on to a discussion about carbon dioxide and hemoglobin. Dissolved carbon dioxide enters the erythrocyte and is hydrated by carbonic anhydrase to form carbonic acid. That immediately dissociates to release a hydrogen ion moiety and bicarbonate. Hydrogen ions bind to the histidine residues on hemoglobin, changing the configuration and nudging hemoglobin into the tense state. This shifts the oxyhemoglobin dissociation curve to the right and releases oxygen. This is known as the Bohr Effect. Approximately 75% of the generated bicarbonate stays in the cell. 25% is pumped out of the cell and swapped with chloride via the chloride bicarbonate exchange protein. This maintains electrical neutrality and it's known as the Hamburger Effect or the Chloride Shift. Now, deoxyhemoglobin has a change in its configuration and it is more receptive to carbon dioxide. CO2 and hydrogen ion equivalents bind to hemoglobin, that's carbaminohemoglobin, and this is known as the Haldane Effect. That's the combination of both the CO2 and the hydrogen ions. Subsequently, the red blood cell that now contains a little bit more carbon dioxide than it did previously travels around the venous side of the circulation into the lungs and surplus CO2 is eliminated. The red blood cell has now arrived in the lungs. Oxygen partial pressure is high in the alveoli and oxygen diffuses into red blood cells while simultaneously dissolved CO2 rapidly diffuses into the air spaces. As oxygen binds to hemoglobin, it increases hemoglobin's affinity for oxygen, shifting it to the relaxed state. The binding of oxygen reduces hemoglobin's affinity for carbon dioxide and hydrogen ions. This is the reverse of the Haldane effect, and CO2 is released from hemoglobin. The released hydrogen ions combine with bicarbonate to form carbonic acid, catalyzed to CO2 and water by carbonic anhydrase. The CO2 diffuses out of the red blood cells into plasma and then into the alveoli for exhalation. The Bohr effect reverses due to rising pH and decreasing CO2, which increases hemoglobin's affinity for oxygen further and stabilizes oxygen binding. No two textbooks or review articles gives the same number for the carbon dioxide content of arterial versus venous blood, but this is my best estimate. The arrow for carbamino hemoglobin reflects the Haldane effect, and venous blood holds about 2 mL per litre more carbon dioxide than arterial blood. The key thing to look at here, though, is the major source of CO2 transport, and that is bicarbonate. Although the rise in venous versus arterial, intracellular and extracellular bicarbonate looks modest, in fact, most of the additional CO2 that is in venous blood is transported as bicarbonate. This is a very unimpressive graph of the percentage of CO2 in arterial and venous blood in different moieties. Zooming in, you can see that there is an 11% increase in both dissolved and hemoglobin-bound carbon dioxide in venous blood. But in reality, the big increase in CO2 content in venous blood is derived from bicarbonate. Now let's look at carbon dioxide and ventilation. Carbon dioxide is produced at a rate of 200 mL or 9 millimoles per minute. CO2 easily passes into the cerebrospinal fluid, where it is converted to carbonic acid, again associated with carbonic anhydrase, and that dissociates to hydrogen and bicarbonate. This lowers the pH and activates chemoreceptors in the ventrolateral medulla. The effect is to increase respiratory drive and alveolar ventilation. One of the major homeostatic processes in the body is to keep the PCO2 in arterial blood at 5.3 kilopascals or 40 millimeters of mercury and the pH at 7.4. So the respiratory center of the brain controls the PCO2, and any increase in PCO2 results in increased alveolar ventilation. Now let's look at what happens with acute hypercarbia. When hypoventilation occurs, for example, during anesthesia or following ingestion of drugs that impair the chemoreceptor control, such as opioids or benzos, or if there is neuromuscular weakness like myasthenia gravis or Guillain-Barré syndrome, or if there is acute respiratory failure due, for example, to severe pneumonia, hypoventilation occurs and carbon dioxide builds up in the body. The total volume of CO2 in the body is about 120 litres. Now compare that to oxygen, where the total oxygen content is about 1.5 litres. There is minimal reserve, but a vast amount of CO2 already present in the system. As a result, even with hypoventilation, CO2 only builds up gradually. But things are very different with hyperventilation. Let me illustrate. This is a famous picture that I've modified from Nunn's respiratory physiology textbook looking at CO2 in the body. At the top is a supply tank that represents metabolic production, and there are 3 different compartments. A fast compartment on the left, which is brain, heart, blood, kidneys, a medium compartment, skeletal muscles, and a slow compartment, fat and bone, and each one of these contains carbon dioxide. The medium and slow compartments have progressively longer time constants versus the fast compartment. Their function is to buffer rapid changes in the fast compartment. The tap on the extreme left-hand side controlled by the little man represents alveolar ventilation. Continuously, we are producing carbon dioxide from the supply tank, and continuously we're wasting it through the tap. In hyperventilation, the tap is turned wide open. As a consequence of this, the fast compartment is rapidly emptied, and then it's backfilled with CO2 from the medium and slow compartments. Regardless, the PaCO2 falls rapidly. In this example, also from Nunn's physiology textbook, we have a graph on the y-axis of the partial pressure of CO2 and on the x-axis of time in minutes. The patient starts off at the little red bar at a PaCO2 of 5.3 kilopascals and 40 millimeters of mercury. And in Nunn's example, the starting point is 3.3 liters minute ventilation. Now we're going to go along and change the ventilator and increase the minute ventilation to 14 liters per minute. Look at what happens with the PaCO2. It drops dramatically and extremely quickly. It falls down to below 20 millimeters of mercury or 2.5 kilopascals. Hyperventilation rapidly reduces PaCO2 in a situation where production of CO2 is at steady state. Now we're going to turn off the tap and make the patient apneic. Note our starting point. The CO2 content of the three compartments has significantly reduced. CO2 is constantly being produced by the tissues, but only at a rate of 200 mils per minute. Over time, the different compartments slowly fill up. In Nunn's model, we revert from the high minute ventilation of 14 liters per minute to the lower starting one of 3.3 liters per minute. Now let us look at what happens following the reduction in the minute ventilation. You will note that the buildup of CO2 is much slower, but look at how long it takes for the CO2 to go back to where we started at 5.3 kilopascals or 40 millimeters of mercury. So the learning point here is that carbon dioxide is produced continuously at 200 mils per minute, depending on metabolic rate. Increasing minute ventilation rapidly clears the extracellular fluid of dissolved carbon dioxide, and that reduces the PaCO2. CO2 is much slower to build up when minute ventilation is reduced because it has to be replaced purely by metabolic activity. It means that clinically, if you make a ventilator change, checking a blood gas, for example, after 10 minutes may be quite misleading. So be careful. If you turn up the minute ventilation, the CO2 will come down fast. If you turn it down, it'll come up very slowly. How much does CO2 rise in apnea? This is very neatly demonstrated by my colleague Craig Lyons a year or two ago. PaCO2 rises 10 millimeters of mercury or 1.3 kilopascals in the first minute because arterial blood becomes venous, and then 3 to 4 millimeters of mercury or 0.5 kilopascals every minute thereafter due to continued metabolic production. So the data that we have from research subjects gives us an idea of what happens if we turn the ventilator off and leave the patient apneic for 10 minutes, but continue to oxygenate them, for example, with high-flow nasal oxygen therapy. What happens is that the CO2 rises by 10 millimeters of mercury or 1.3 kilopascals in the first minute, and then by 3.75 millimeters of mercury or 0.5 kilopascals every minute thereafter. So after 10 minutes, the PaCO2 will have risen by 44 millimeters of mercury, or 5.8 kilopascals, to a total of 84 millimeters of mercury, or 11 kilopascals. And this means that in apnea, the PaCO2 doubles in 9 minutes. Although apnea is not a common phenomenon outside of anesthesia, hypoventilation is. We see it in acute respiratory failure, particularly in COPD. We see it with myasthenia gravis, Guillain-Barré syndrome. We see it with stroke. We see it with overdoses with opioids. So I'm going to give you an example of a situation where a patient hypoventilates. So we start off with a patient with a normal partial pressure of CO2 in their blood of 5.3 kilopascals, or 40 millimeters of mercury. And then we're going to hypoventilate that patient to 8 kilopascals, or 60 millimeters of mercury, and keep the CO2 at that level. Now, I'm aware that there are people watching these videos who use kilopascals as their main way of measuring CO2, and people who use millimeters of mercury as their major way of measuring CO2. So I've provided you with two graphs. They're actually identical, but they use different numbers. On the left-hand side, we have the PCO2 and the bicarbonate in kilopascals and millimoles per liter. And on the right-hand side, we have the CO2 in millimeters of mercury and the bicarbonate millimoles per liter. So even though the CO2 looks different from one to the other, just multiply the kilopascals by 7.5. The bicarbonate is the same, but I've kept the color slightly differently so you don't get confused. And this is where we are at baseline. And the bicarbonate is 24 millimoles per liter at 5.3 kilopascals, or 40 millimeters of mercury. Now we're going to hypoventilate our patient to 8 kilopascals, or 60 millimeters of mercury, for a couple of hours. And let's see what happens to the bicarbonate. We started at 24 millimoles per liter, but it's gone up now to 26 millimoles per liter. A small but not insignificant rise. Now let's roll this on to 72 hours, that's 3 days, keeping the patient at that same partial pressure of CO2 on the blood gas. And let's see what happens to the bicarbonate. Now you can see that the bicarbonate has gone up quite substantially. We went from 24 to 26, and now the bicarbonate is 32 millimoles per liter. So it has risen quite substantially from that baseline by 8 millimoles per liter. The reason for this is the patient is now at a steady state for CO2 production, CO2 elimination, and bicarbonate concentration. This is the appropriate bicarbonate concentration for a PCO2 of 8 kilopascals, or 60 millimeters of mercury. And there is a rule of thumb for calculating this out. In acute hypercarbia, the bicarbonate increases by 1 millimole per liter for every 10 millimeters of mercury, or 1.3 kilopascals increase in the PaCO2. This is the calculation for how you do this. The change in the bicarbonate is 0.1 times the change in the PaCO2 in millimoles per millimeter of mercury, or 0.75 times the change in PaCO2 in millimoles per liter per kilopascal. If the PaCO2 goes from 40 to 60 millimeters of mercury, 5.3 to 8 kilopascals, then the bicarbonate will increase by 2 millimoles per liter to 26 millimoles per liter. In chronic steady-state hypercarbia, the bicarbonate increases by 4 to 5 millimoles per liter for every 10 millimeters of mercury, or 1.3 kilopascals increase in the PaCO2. The calculation is the change in the bicarbonate is 0.4 times the change in the PaCO2 in millimoles per millimeter of mercury, or 3 times the PaCO2 change in millimoles per liter per kPa. So if the PaCO2 goes from 40 to 60, or 5.3 to 8 kilopascals, then the bicarbonate moves in significantly greater increments. It increases by 8 millimoles per liter to 32 millimoles per liter. So these rules of thumb are really important when you're looking at acid-base balance, and we're going to talk about that in the next tutorial. In the meantime, let's review this tutorial. This was a tutorial about carbon dioxide content of extracellular fluid, red blood cells, and plasma, and the delivery of carbon dioxide from the tissues to the lungs. I discussed the role of carbon dioxide in metabolism. Carbohydrates, proteins, and fats all end up in the Krebs cycle, and they generate carbon dioxide and energy. I discussed the diffusion characteristics of carbon dioxide. Carbon dioxide is far more diffusible than oxygen. As a consequence, all of our tissues are saturated in CO2. We looked at the interaction between carbon dioxide and hemoglobin, the Bohr and Haldane effect, and how these occur in the tissues where they help load carbon dioxide into hemoglobin, and back in the lungs where the impact of oxygen causes the unloading of CO2 and the loading of oxygen onto hemoglobin, and the shifting of the oxyhemoglobin dissociation curve to the right in the tissues and to the left in the lungs. How carbon dioxide falls rapidly with increased minute ventilation and rises slowly with reduced minute ventilation. And finally, we looked at hypercarbia and bicarbonate, how it's different in the acute phase versus the chronic phase, in other words, after a couple of days of continuous hypoventilation. In the next tutorial, we're going to look at the impact of carbon dioxide on acid-base balance. I guarantee you'll learn something.